Hi and welcome to this higher level applied maths video where we're going to look at difference versus differential equations. So in this video, we're going to explore the similarities and differences between difference and differential equations. We're going to understand or try to understand the difference between discrete and continuous. We're going to use difference equations to model population, and at the same time then we're going to look at how differential equations could be done to model the same population change but on a continuous basis. And we're going to compare the predictions made by each model. So the video really is only suitable for higher level applied math students, as differential equations are only examined at higher level. So we're going to look at two different examples in this video. We're going to look at the 2023 Deferred Higher Level question 2 part B, and we're going to look at the SEC sample higher level paper, which is question 8. So before we jump into our examples, we're going to explore the key differences and similarities between difference and differential equations. For us in applied maths, this all falls under the study of how things change. So difference equations, we talk about these being discrete changes. So that means that any adding or subtracting is done on a regular or at irregular intervals. That could be on a monthly basis, on an annual basis, or so on. For differential equations, this is a continuous change. So this is the changes happening all of the time. So in real world, we can use difference equations for population, but it is more common for things like interest and loan payments and supply and demand, because that allows us to really see that discrete change. And then we can see it with population growth models. And for differential equations, we can see this for like cooling and warming, radioactive decay, acceleration. So think about where our change is happening continuously, where it's not jumps, where it's happening quite smoothly. So then they're both the same in the sense that they can both be used to predict and analyze how systems evolve over time. So not all will be suitable for all scenarios. There are definitely scenarios that difference equations are better for, like we said, interest and loan payments. And there's definitely scenarios where differential equations are more appropriate. So think of like warming, cooling, and so on. However, there are situations where either could be used, so things like population. And as we're working with this, we'll try and make sense of what might be the indicators of a problem where either difference or differential equations can be used. So one of the things we talk about a lot when we try to compare and contrast difference and differential equations is the idea of discrete versus continuous. Now you might have met those words elsewhere. We often talk about discrete data versus continuous data when we're looking at statistics, even at junior cycle. But to make sense of it, discrete change means that the change is occurring at distinct steps or intervals, so regular times. So think of any data where the jumps will happen and you don't see any change in between the jumps. So for example, if you're paying off a loan, you owe €100, you pay off €10, you now owe 90. It didn't go 100, 99, 98, and so on. It didn't go down through all the steps. It was quite discrete. So another example would be a population that grows only at the end of each year, or money added to a bank account each month. So for us, when we have a discrete change, we're using difference equations. So they're perfect for modeling anything that is discrete. When we talk about continuous change, we mean a change that's happening quite smoothly over time without distinct breaks, allowing for ongoing gradual evolution. So for example, if we just think about continuous data, we would have things like height or weight, because you have to work through all the bits in between. So if I measure you today and I measure you in a year's time and you've grown taller, that has been continuous. You didn't just wake up taller one day, you've had to grow through all of those heights. An example for what we're working with here is temperature. So temperature is where if there's a change in temperature, you have to work through all of the temperature. So if it gets hot during the day, we wake up and it's 10 degrees and by midday it's 20 degrees, it didn't just magically turn to 20 degrees. The thermometer, if you can imagine it, it would have to change continuously or smoothly. So things that tend to be continuous are things we measure. So things like weight, height, temperature, anything with measurement will give us a hint towards continuous. And then for us, if we're working with continuous change, we're talking with we're using differential equations, because calculus is the way that we're able to work with these smooth, continuous changes. So the key distinction, it's like discrete is steps, continuous is smooth. Okay, so really think about that, and choosing the right model depends on whether the system evolves in intervals, so if it's discrete, or flows continuously over time, so that will be continuous. So the majority of our questions are very clear about what we have between difference versus differential equations, but it's good for you to understand the difference between them if you did have to identify which will be the optimal mathematical tool to use in a question. Example 1 is coming from the 2023 Deferred Higher Level Paper, and it's question 2, part B. In another larger computer network, a message travels from one computer to another in the network. Each time a message travels from one computer to the next, the number of errors in the message E increases by 15%. However, C errors are corrected each time the message travels. The number of computers the message travels to is counted using the number n. A message starts at computer n equals 0 and travels on a linear path through the computer network. E, the number of errors in the message, may be modeled by the difference equation En plus 1 is equal to 1.15 En minus C. Where n is greater than or equal to 0 and n is an element of z, so it's an integer. There are 101 errors in the message when it leaves the computer, i.e. e to the power 0, E0 is equal to 101. So part 1 asks us to solve this difference equation and find an expression for En in terms of n and c. So this is a first order difference equation and it's given in this form. So when we have it in the form Tn plus 1 equals Atn plus b, so we can see here, there's my n, here's my b, then our general solution can be written as, in this case, it's En, so b, which is minus c, 1 minus a, which is 1.15 to the power of n, all over 1 minus 1.15. plus a, which is 1.15 to the power of n, and t0, which in this case is e0, which is 101. So it would be good practice to do a little bit of tidying up here. So that bottom line, 1 minus 1.15, leaves us with a negative 0.15 underneath, and that can tidy up. So let's do that bit first. 1 minus 1.15 to the power of n, and it can be tidied up as a fraction, which we're going to do now, and that's negative plus, and I'm going to just write that 101 1.15 to the power of n here. So that negative, they both become positive, and then instead of 0.15, instead of dividing by 0.15, we end up multiplying by the reciprocal of that fraction. So 0.15 is 3 over 20, and then when we flip that, that's going to give us 20c, 1 minus 1.15 to the power of n, all over 3. You can pull that 3 out in front if you prefer. And then we've 101 1.15 to the power of n. You can do more cleanup on it if you want. It's not going to clean up nice and tidy with that c. If that c was a number, we would absolutely tidy it up in a little bit more, in a nicer way, to group together the 1.15 to the power of n. So now that we have that, which is our answer for part 1, the second part then says, it is found that the message contains 0 errors after it reaches the 21st computer, i.e. E21 is equal to 0. Calculate the value of C. So we know E21 equals 0. So E21 is going to be 20C all over 3, 1 minus 1.15 to the power of 21 plus 101, 1.15 to the power of 21, and that's all going to equal 0. We want to solve for c, so let's bring everything across the equals. So the first thing I'm going to bring over is that 101, so that's going to give me minus 101, 1.15 to the power of 21. You can put that into the calculator and get a decimal for it. I'm going to wait till the end to do the calculator work. So then after we bring that over, this part comes over. Because that's effectively multiplied by the 20c over 3, when we bring it across, we're going to divide. So 15 to the power of 21. And then the final step will be to deal with the 20 over 3, which means we are going to be left with c equals 3 times the minus 101, 1.15 to the power of 21, all over 20 times 1 minus 1.15 to the, sorry, that 21 is inside our bracket, 21. And then this is going to be to the nearest whole number. We go put that into the calculator. We get 16.00009593, which to the nearest whole number is going to be 16. Now, the third part of this question then tells us that E can also be modelled using a differential equation. So write a differential equation, dE dN, the rate of change of E with respect to N in terms of E and C. Okay, so the important thing to remember when we're dealing with the differential equation, when we have dE dN, what we're actually talking about is the change in E over the change in N. It is a rate of change. That triangle is a delta symbol. It just means change. So we're only focusing on the change, as opposed to when we're dealing with the differential equation, we're saying 1.15. So although it increases by 15%, we say by the time we get to the next computer, there will be 100%, the last number we had, plus an extra 15%. That's how difference equations work. We deal with the total. However, for differential equations, we talk about just the change. So we're talking about the change in error given the change in with respect to N, so with the change of the number of computers that it meets. So that means we're just going to have 15%, and it's an increase, which makes it positive. So we have a plus 0.15 times the error, which we're just going to call E. So it doesn't have a subscript like when we have difference equations. But then that's not the only thing that happens. Remember, C errors are corrected, so we then take away that C. And that's all we're being asked to do in that part, to create that differential equation. It's really important to understand the key differences here between our differential equation and our difference equation. And in particular, really think about that differential equation focuses on the change. It's the rate of change. It's how things are changing. It's not giving us a total answer. So example 2 comes from our sample higher level paper, and it's question 8. And this was a full question where we were exploring both difference equations and differential equations. A group of scientists are investigating the population P of rabbits on a certain island. They estimate that there are 8,000 rabbits on the island and that the population is growing at a constant rate of 3% per year. The scientists plan to remove a number of rabbits from the island every year to help populate another habitat. They develop mathematical models to predict how P, the population, will change if B rabbits are removed from the island every year. The first model, which the scientists develop, uses a difference equation to express the population of rabbits in the year n+1 in terms of the population in year n. The difference equation is Pn plus 1 is equal to 1.03 Pn minus B, where n is greater than or equal to 0, n is an element of z, which means it's an integer, and P0 equals 8,000. Solve this difference equation to find an expression Pn in terms of n and b. So the first thing to note is that we have a first order difference equation in this form. So our form is Tn plus 1 equals A Tn plus B. So here is my A and here is our B. So that means to solve this, we get Pn equals B, which is minus B. Watch your sign with that. 1 minus A, which is 1.03 to the power of n, all over 1 minus 1.03 plus 1.03 to the power of n times T0, which in this case is our P0, which is 8,000. Now we want to do a little bit of cleanup with this. So I'm going to tidy up the bottom of the fraction. And that's going to give us a negative 0.3. And then the negative on the top and the bottom will undo each other. We're left with just B over 0.03 plus 1.03 to the power of n times 8,000. Now, if that B were a number, I'd go further with my cleanup. We can turn it into a fraction, and that's 0.03 on the bottom. So 0.03 is 3 over 100. So then instead of dividing by 3 over 100, we can multiply by 100 over 3. So we get 100 B all over 3, 1 minus 1.03 to the power of n plus, and then we get our 8,000, 1.03 to the power of n. Like I said, if that B were a number, I'd work it further and bring the 1.03 to the power of n back together. A second model, which the scientists developed, uses a differential equation to express the rate of change of P with respect to n, the time measured in years. So the differential equation is dP dN equals 0.03p minus b. Again, we can notice that unlike the difference equation, in the differential equation, we have 0.03 and not a 1.03. Remember, when we talk about our differential equation, so we're talking about a rate of change, we're focusing only on the change, not on the final answer. So we're being asked to solve this differential equation. So we have dP dN, and that's 0.03 P minus B. So this is a first order because we only have a first derivative, so dP dN. What we want to do is we want to bring P's over one side and anything else over the other side. This has to be done with multiplication or division, because in order to integrate, which is our next step, we need to have everything on each side either multiplied by the dP if it's on the left or by the dN if it's on the right. So what I'm going to do is I'm going to bring over this whole thing. And because I'm bringing the whole thing over, I'm going to effectively divide by it. So that gives us 1 over 0.03p minus b, and that's all going to be with respect to p, so dp, and then I've brought the dn over the other side. We're going to now integrate both sides. I'm going to use limits of integration here. On the left hand side of the population, and the population is going to be 8,000 when n the time is 0. To find the answer, so solving this differential equation, we're going to get an answer that looks like P equals, so I need to keep P in it. So P and N go on the top. This will mean we don't have to work with the plus C. Instead, we can go straight to getting our final answer. It's a nice efficient way to work. I've linked the differential equation videos in the description below if you need to do a bit more revision on those. So our checklist when we have any kind of integration is, first of all, is there a formula on page 26? Now this is a special one on page 26. There are 3 main formulas that we tend to see that are the chain rule kind of worked backwards and simply, and this is one of them, and this is 1 over x integrates to ln x. So this is ln 0.03p minus b, but we end up dividing by the derivative of the inner function, where that inner function is what's inside the ln. So when we differentiate that, we get 0.03. The p disappears, that's a coefficient of p, so think of we're differentiating that, so it's the derivative of the inner function, and minus b is a constant, so that disappears. We're going to evaluate that between p and 8,000. On the right hand side, dn integrates to simply n, and we're going to deal with that between 0 and n. So this gives us ln 0.03p minus b, that's all over 0.03, minus ln 0.03 times 8,000 minus b, all over 0.03, and that's all going to equal n minus 0, which is just n. So I'm going to multiply everything by that 0.03 to get rid of the fractions. That gives me ln 0.03p minus b minus ln, let's multiply these two together. That gives us 240 minus b, and that equals 0.03n. Remember, the goal of solving differential equation is to get this in the form p equals. So we're going to get the p on one side, and anything that's not a p, we're going to bring it across. So that includes this ln. So I have 0.03n plus ln 240 minus b. So in order to get rid of the natural log, I'm going to put each side as a power of e, so e to the power of ln, and that will undo itself. On the right hand side, it's e to the full side. You can use the idea of our movement between logs and exponentials, however you want to work. This is a nice little quick way to do it. So 0.03p minus b equals e to the power of 0.03n. Now, we're going to use the first rule of indices here. The power, so that's my power of e. The powers are added together, meaning we can break that out into e to the power of 0.03n and e to the power of ln 240 minus b. The reason that's so important to do is because this e and ln can undo each other as well. So what we're left with is 0.03p minus b equals, now we have 240 minus b, and that's all multiplied by e to the power of 0.03 n. We're going to bring our b across. So p equals 240 minus b e to the power of 0.03 n, add a b, and then our last step is to multiply that by 0.03p. So just giving us a little bit more space here to work to get p on its own, I'm going to bring across the 0.03, the coefficient, 0.03 n plus b, and just put it all over here. You can do a little bit more cleanup. Again, if we knew the value of b, we could clean it up. It's absolutely perfect to present that 0.03 instead of being a decimal as a fraction, so 3 over 100. Again, dividing by 3 over 100 multiplies by 100 over 3. So absolutely fine to give your answer in any form. So then part 3 asks us to work with both models. So we have the difference equation model that we started with and the differential equation model. So the scientists want to know what each model predicts the rabbit population on the island will be after 50 years if 200 rabbits are removed each year. So calculate P50 from the first model, so that's our difference equation model, and P of 50 using the second model when B equals 200. So here are our two models. So this one came from part 1 and this one came from part 2. And all we're working with now is we've been told that B is 200, that's for both. And we want to also plug in 50 in lieu of N. So here we have 100 times 200 all over 3, 1 minus 1.03 to the power of 50 plus 1.03 to the power of 50 times 8,000. And according to then that first model, the number of rabbits will be, putting this into the calculator, 12,512. For our second model, we're going to do P of 50. Again, N becomes 50 and B is still 200. 0.03 times 50. This whole thing is multiplied by 240 minus 200 plus B, which is plus a 200, all over 0.03. Again, putting that into the calculator to figure out for model 2, it tells us 12,642 rabbits. So quite close together given the size of those numbers. So we can see how both models have been used to get the same or to do the same predicting. The difference being that the difference equation model assumes that the change is discrete. It happens each year, while the second model, the difference equation model, assumes that it's continuous. So each of these models makes a different assumption about the removal of rabbits from the island. What are the two different assumptions? So the difference equation model assumes that the removal of rabbits is happening at the end of each year after the population has grown. We talked about this at the start of the video, the idea of difference equations being discrete. The changes are happening at incremental times. While for the differential equation model, it assumes that the rabbits being removed is happening throughout the year. So that could be better suited to a scenario where the rabbits are maybe dying off due to disease or are being eaten by predators or so on, while the difference equation model might be more suitable in a case where the rabbits are being physically removed at a given point in the year by the scientists. So the last part of this question, the scientists want to know what value of B should be chosen so as to keep the rabbit population on the island constant. Calculate this value of B using either model. So because we see more of it, I'm going to use the difference equation model, which looks like this. And basically, if we have a constant, it means that the population won't change year on year. And in simple terms, it means that Pn is equal to Pn plus 1 or Pn minus 1, whatever way we want to work it. So if I equate Pn equals to Pn plus 1, I get something like this. So basically I need to figure out our value for B. So I'm going to simplify this by saying let's multiply both sides by 3, which gets rid of our fraction. And then there's a plus 10b that's being added to both sides, so that'll effectively undo each other. There is a 100 that's there. So what that leaves us with is 1.03 to the power of n. Notice how this bracket matches this bracket. But if I were to cancel those off on each side, I'd basically be left with this. So I'll get rid of those brackets, and that can never be the case. So the only way that those two could be considered equal would be if I multiply both sides by 0, because then I get 0 equals 0. So the only way that that could be true was if this were 0, and the only way to make them 0 is by looking at that bracket. So the 100 that we cancelled off was fine because 100 is 100, it's not 0. So what we need to think about is, okay, right now we have 1.03 to the power of n times 240 minus b, and we want to know when this is equal. So 0.3 to the power of n plus 1, 240 minus b. We've already said the only way that this and this, they'll never be equal. So the only way that these two sides can be made equal were if they were both multiplied by a 0. So what we have come to this conclusion is, well, the only way this would work is if 240 minus b gave us a 0. And in that case, the value of b that would make that happen will be 200 and 40. So that is using our difference equation to work it through. A nice straightforward question. You can do it in more of kind of a theory way, but I like to look at the formula and really make sense of it. Remember, only the b can change because we're looking for a value of b. Any constants are, by their name and their definition, they are constant, they cannot change. So we have to look at the bit that is going to vary based on the value of b. I hope you found this video useful. Thank you so much for watching. More videos are linked in the description below, but if you have any suggestions for content, please leave me a comment below.